So I'd like to get started. So today we're going to talk about CNNs in practice and talk about a lot of really low-level sort of implementation details that are really common to get these things to work when you're actually training things. But first, as usual, we have some administrative stuff to talk about. Number one is that through a really heroic effort by all the TAs, all the midterms are already graded, so you guys should definitely thank them for that. And you can either pick them up after class today or in any of these office hours that are up here. Also, keep in mind that your project milestones are going to be due tonight at midnight. So make sure that, I hope you've been working on your projects for the last week or so and have made some really exciting progress. So make sure to write that up and put it in the assignments tab on Dropbox. No, not on Dropbox. Put it on the assignments tab on coursework. Sorry, I know this has been really confusing, but assignments tab just like assignment 2. Assignment 2, we're working on grading. Hopefully we'll have that done sometime this week-ish. And remember that assignment 3 is out. So how's that been going? Anyone done? OK, that's good. One person's done. So the rest of you should get started because it's due in a week. So we have some fun stats from the midterm. So don't freak out when you see your grade, because we actually had this really nice, beautiful Gaussian distribution with a beautiful standard deviation. We don't need to batch normalize this thing. It's already perfect. I'd also like to point out that someone got a max score of 103, which means they got everything right and the bonus. So that means it wasn't hard enough, maybe. We also have some per question stats, like per question breakdown on average score per every single question in the midterm. So if you got something wrong and you want to see if everyone else got it wrong too, you can go check on these stats later on your own time. But we have stats for the true-false and the multiple choice. Keep in mind, so actually for 2 of the true-false, we decided during grading that they were a little bit unfair. We threw it out and just gave you all the points, which is why 2 of those are at 100%. We have these stats for all the individual questions, so go ahead and have fun with those later. So last time, I know it's been a while that we had a midterm and we had a holiday, but if you can remember, like over a week ago, we were talking about recurrent networks. So we talked about how recurrent networks can be used for modeling sequences. You know, normally with these feed-forward networks, they model this feed-forward function. But these recurrent networks, we talked about how they can model different kinds of sequence problems. We talked about 2 particular implementations of recurrent networks, vanilla RNNs and LSTMs. And you'll implement both of those on the assignment, so you should know what they are. We talked about how these recurrent neural networks can be used for language models, and had some fun showing some sample generated text on, what is this, Shakespeare and algebraic geometry, so that's fun. We talked about how we can combine recurrent networks with convolutional networks to do image captioning. And we played a little bit this game of being RNN neuroscientists and diving into the cells of the RNNs and trying to interpret what they're doing. And we saw that sometimes we have these interpretable cells that are, for example, activating inside if statements, which is pretty cool. But today we're going to talk about something completely different. There are 3, we're going to talk about really a lot of low-level things that you need to know to get CNNs working in practice. So there's 3 major themes. It's a little bit of a potpourri, but we're going to try to tie it together. So the first is really squeezing all the juice that you can out of your data. So I know a lot of you, especially for your projects, you don't have large data sets. So we're going to talk about data augmentation and transfer learning, which are 2 really powerful, useful techniques, especially when you're working with small data sets. We're going to really dive deep into convolutions and talk a lot more about those, both how you can design efficient architectures using convolutions, and also how convolutions are efficiently implemented in practice. And then finally, we're going to talk about something that usually gets lumped under implementation details and doesn't even make it into papers. But that's stuff like what is a CPU, what is a GPU, what kind of bottlenecks do you experience in training, how much you distribute training over multiple devices. So that's a lot of stuff. We should get started. So first, let's talk about data augmentation. I think we've sort of mentioned this maybe in passing so far in the lectures, but never really talked formally about it. So normally when you're training CNNs, you're really familiar with this type of pipeline. During training, you're going to load images and labels up off the disk. You're going to pipe the image through to your CNN. Then you're going to use the image together with the label to compute some loss function, then backpropagate and update the CNN and repeat forever. So that you should be really familiar with that by now. The thing about data augmentation is we just add one little step to this pipeline, which is here. So after we load the image up off disk, we're going to transform it in some way before passing it to the CNN. And this transformation should preserve the label. So we're going to compute loss, backpropagate, and update the CNN. So it's really simple, and the trick is just what kinds of transforms you should be using. Right, so data augmentation, the idea is really simple. It's sort of this way that lets you artificially expand your training set through clever usage of different kinds of transformations. So if you remember, the computer is really seeing these images as these giant grids of pixels. And there are these different kinds of transformations we can make that should preserve the label, but which will change all of the pixels. If you imagine like shifting that cat one pixel to the left, it's still a cat, but all the pixels are going to change. So when you talk about data augmentation, you're sort of imagine that you're expanding your training set. These new fake training examples will be correlated, but it'll still help you train models with bigger models with less overfitting. And this is very, very widely used in practice. Pretty much any CNN you see that's winning competitions or doing well on benchmarks is using some form of data augmentation. So the easiest form of data augmentation is horizontal flipping. If we take this cat and we look at the mirror image should still be a cat. And this is really, really easy to implement. In NumPy, you can just do it with a single call, a single line of code. Similarly easy in Torch, other frameworks. This is really easy, very widely used. Something else that's very widely used is to take random crops from the training images. So at training time, we're going to load up our image, and we're going to take a patch of that image at a random scale and location, resize it to our fixed whatever size our CNN is expecting, and then use that as our training example. And again, this is very, very widely used. Just to give you a flavor of how exactly this is used, I looked up the details for ResNets. So they actually, at training time, each training image, they first pick a random number, resize the whole image so that the shorter side is that number, then sample a random 224 by 224 crop from the resized image, and then use that as their training example. So that's pretty easy to implement and usually helps quite a bit. So when you're using this form of data augmentation, usually things change a little bit at test time. So at training time, when you're using this form of data augmentation, the network is not really trained on full images. It's trained on these crops. So it doesn't really make sense or seem fair to try to force the network to look at whole images at test time. So usually in practice, when you're doing this kind of random cropping for data augmentation, at test time, you'll have some fixed set of crops and use these for testing. So very commonly, you'll see 10 crops. You'll take the upper left-hand corner, the upper right-hand corner, the two bottom corners, and the center. That gives you 5. Together with their horizontal flips gives you 10. So you'll take those 10 crops at test time, pass them through the network, and average the scores of those 10 crops. So ResNet actually takes this a little bit one step further, and they actually do multiple scales at test time as well. So this is something that tends to help performance in practice, and again, very easy to implement, very widely used. Another thing that we usually do for data augmentation is color jittering. So if you take this picture of a cat, maybe it was a little bit cloudier that day or a little bit sunnier that day. And if we would have taken a picture, then a lot of the colors would have been quite different. So one thing that's very common to do is just change the color a little bit of our training images before we feed it to the CNN. So a very simple way is just to change the contrast. This is, again, very easy to implement, very simple to do. But actually, in practice, you'll see that this contrast jittering is a little bit less common. And what instead you see is this slightly more complex pipeline using principal component analysis over all the pixels of the training data. So the idea is that for each pixel in the training data is this vector of length 3, an RGB. And if we collect those pixels over the entire training data set, you get a sense of what kinds of colors generally exist in the training data. Then using principal component analysis gives us 3 principal component directions in color space that kind of tell us what are the directions along which color tends to vary in the data set. So then at training time for color augmentation, we can actually use these principal components of the color of the training set to choose exactly how to jitter the color at training time. This is, again, a little bit more complicated, but it is pretty widely used. So this type of PCA-driven data augmentation for color, I think was introduced with the AlexNet paper in 2012, and it's also used in ResNet, for example. So data augmentation is really this very general thing, right? You just want to think about, for your data set, what kinds of transformations do you want your classifier to be invariant to? And then you want to introduce those types of variations to your training data at training time. And you can really go crazy here and get creative and really think about your data and what types of invariances make sense for your data. So you might want to try like maybe random rotations, depending on your data. Maybe rotations of a couple degrees make sense. You could try like different kinds of stretching and shearing to simulate maybe affine transformations of your data. And you could really go crazy here and try to get creative and think of interesting ways to augment your data. Another thing that I'd like to point out is this idea of data augmentation really fits into kind of a larger theme that now we've seen repeated many times throughout the course. And this theme is that one way that's really useful in practice for preventing overfitting as a regularizer is that during the forward pass, during training, when we're training our network, we add some kind of weird stochastic noise to kind of mess with the network. For example, with data augmentation, we're actually modifying the training data that we put into the network. With things like dropout or drop connect, you're taking random parts of the network and either setting the activations or the weights to 0 randomly. This also appears kind of with batch normalization, since with batch normalization, your normalization contents depend on the other things in the mini batch. So and during training, the same image might end up appearing in mini batches with different other images. So that actually introduces this type of noise at training time. But in all of these examples, at test time, we average out this noise. So for data augmentation, we'll take averages over many different samples of the training data. For dropout and drop connect, you can sort of evaluate and marginalize this out more analytically. And for batch normalization, we keep these running means. So I just think that's kind of a nice way to unify a lot of these ideas for regularization, is that when you can add noise at the forward pass and then marginalize over it at test time. So maybe keep that in mind if you're trying to come up with other creative ways to regularize your networks. So the main takeaways for data augmentation are that, one, it's usually really simple to implement. So you should almost always be using it. There's not really any excuse not to. It's very, very useful, especially for small data sets, which I think many of you are using for your projects. And it also fits in nicely with this framework of noise at training and marginalization at test time. So I think that's pretty much all there is to say about data augmentation. So if there's any questions about that, I'm happy to talk about it now. Yeah?
Do you typically pre-compute your augmented data set, or do you resample live as you're training?
Yeah, that's a good question. So a lot of times you'll actually resample it live at training time, because it would take a lot of disk space to kind of dump these things to disk. So sometimes people get creative and even have like background threads that are fetching data and performing the augmentation. All right. So if that's clear, we can talk about the next idea. So there's this myth floating around that when you work with CNNs, you really need a lot of data. But it turns out that with transfer learning, this myth is busted. So there's this really simple recipe that you can use for transfer learning. And that's, first, you take whatever your favorite CNN architecture is, be it AlexNet or VGG or what have you, and you either train it on ImageNet yourself, or more commonly, you download a pre-trained model from the internet. That's easy to do. Just takes a couple minutes to download, many hours to train, but you probably won't do that part. Next, there's sort of two general cases. One, if your data set is really small and you really don't have any images whatsoever, then you can just treat this classifier as a fixed feature extractor. So one way to look at this is that you'll take the last layer of the network, the softmax, if it's an ImageNet classification model, you'll take it away, and you'll replace it with some kind of linear classifier for the task that you actually care about. And now you'll freeze the rest of the network and retrain only that top layer. So this is sort of equivalent to just training a linear classifier directly on top of features extracted from the network. So what you'll see a lot of times in practice for this case is that sort of as a pre-processing step, you'll just dump features to disk for all of your training images and then work entirely on top of those cached features. So that can help speed things up quite a bit. And that's quite easy to use. It's very, very common. It usually provides a very strong baseline for a lot of problems that you might encounter in practice. And if you have a little bit more data, then you can actually afford to train more complex models. So depending on the size of your data set, usually you'll freeze some parts, some of the lower layers of the network, and then instead of retraining only the last layer, you'll pick some number of the last layers to train, depending on how large your data set is. And generally, when you have a larger data set available for training, you can afford to train more of these final layers. And again, if you're similar to the trick over here, what you'll see very commonly is that instead of actually explicitly computing this part, you'll just dump these last layer features to disk and then work on this part in memory. So that can speed things up quite a lot. And sometimes, oh, yeah, question?
What would you consider to be like a small or a medium-sized data set?
You basically have to try it and see. But especially for this type of small data set, we'll work on instances. So if you had, if you want to just do image retrieval, a pretty strong baseline is just to use L2 distance on CNN features. So this type of approach, I mean, however many samples you expect to need to train like an SVM or something. And for these, if you have more data than you would expect to need for an SVM, then try that. So that's a little hand wavy. I'm sorry. Yeah?
So you still need all the weights for each layer, because you still run it through the forward pass. You just don't do the back propagation to update.
It depends. Sometimes you actually will run through the forward pass, but sometimes you'll just run the forward pass once and dump these to disk. That's pretty common actually, because then it saves compute. Yeah.
Actually, going off that question, so when you're freezing a certain part of the network, does that then mean that retraining on the part that you actually care about just means like you're back propagating only the part of the loss?
Yeah. Yeah. So then typically this final layer you'll always need to swap in and reinitialize from random because you'll probably have different classes or you're doing a regression problem or something. But then these other intermediate layers you'll initialize from whatever was in the pre-trained model. And actually, in practice, when you're fine-tuning, a nice tip to actually do this is that there'll really be two types of layers three types of layers when you're fine-tuning. There'll be the frozen layers, which you can think of as having a learning rate of 0. There are these new layers that you've reinitialized from scratch. And typically, those have maybe a higher learning rate, but not too high, maybe 1/10 of what your network was originally trained with. And then you'll have these intermediate layers that you are initializing from the pre-trained network, but you're planning to modify during optimization and fine-tuning. So these intermediate layers, you'll tend to have a very small learning rate, maybe 1/100th of the original. Yeah?
Will this only work if your task is roughly similar to what the lower levels were trained for?
That's a good question. Some people have tried to investigate that and found that generally fine-tuning, this type of transfer learning fine-tuning approach works better when the network was originally trained with similar types of data, whatever that means. But in fact, these very low-level features are things like edges and colors and Gabor filters, which are probably going to be applicable to just about any type of visual data. So especially these lower-level features, I think, are generally pretty applicable to almost anything. And by the way, another tip that you sometimes see in practice for fine-tuning is that you might actually have a multi-stage approach, where first you freeze the entire network, and then only train this last layer. And then after this last layer seems to be converging, then go back and actually fine-tune these. You can sometimes have this problem that because this last layer is initialized randomly, you might have very large gradients that kind of mess up this initialization. So the two ways that we get around that are either freezing this at first and letting this converge, or by having this varying learning rate between the two regimes of the network. So this idea of transfer learning actually works really well. So there was a couple pretty early papers from 2013, 2014, when CNNs first started getting popular. This one in particular, the astounding baseline paper, was pretty cool. What they did is they took what at the time was one of the best CNNs out there, was overfeet. So they just extracted features from overfeet and applied these features to a bunch of different standard data sets and standard problems in computer vision. And they compared these, right? So then the idea is that they compared against what was, at the time, these very specialized pipelines and very specialized architectures for each individual problem and data set. And for each problem, they just replaced this very specialized pipeline with very simple linear models on top of features from overfeed. And they did this for a whole bunch of different data sets and found that in general, overall, these overfeed features were a very, very strong baseline. And for some problems, they were actually better than the existing methods. And for some problems, they were a little bit worse, but still quite competitive. So this was, I think, a really cool paper that just demonstrated that these are really strong features that can be used in a lot of different tasks and tend to work quite well. Another paper along those lines was from Berkeley, the decaf paper. And decaf later became caffeinated and became cafe. So that's, that's kind of the lineage there. So kind of the recipe for transfer learning is that you should kind of think about this little 2x2 matrix. How similar is your data set to what the pre-trained model was? And how much data do you have? And what should you do in those 4 different columns? So generally, if you have a very similar data set and very little data, just using the network as a fixed feature extractor and training simple, maybe linear models on top of those features tends to work very well. If you have a little bit more data, then you can try fine-tuning and try actually initializing the network from pre-trained weights and running the optimization from there. This other column is a little trickier. In this box, you might be in trouble. You can try to get creative, and maybe instead of extracting features from the very last layer, you might try extracting features from different layers of the convnet. And that can sometimes help. The intuition there is that maybe for something like MRI data, probably these very top-level features are very specific to ImageNet categories, but these very low-level features are things like edges and stuff like that that might be more transferable to non-ImageNet type data sets. And obviously, in this box, you're in better shape, and again, you can just sort of initialize and fine-tune. So another thing I'd like to point out is this idea of initializing with pre-trained models and fine-tuning is actually not the exception. This is pretty much standard practice in almost any larger system that you'll see in computer vision these days. And we've actually seen 2 examples of this already in the course. So for example, if you remember from a few lectures ago, we talked about object detection, where we had a CNN looking at the image and region proposals and all this crazy stuff. But this part was a CNN looking at the image. And for image captioning, we had a CNN looking at the image. So in both of those cases, those CNNs were initialized from ImageNet models. And that really helps to solve these other more specialized problems, even without gigantic data sets. And also for the image captioning model in particular, part of this model includes these word embeddings that you should have seen by now on the homework if you started on it. But those word vectors, you can actually initialize from something else that was maybe pre-trained on a bunch of text. And that can sometimes help maybe in some situations where you might not have a lot of captioning data available. Yeah?
On the previous slide, has anybody tried collecting features from multiple layers and concatenating them?
So that was like on here or maybe here. Yeah, people have definitely tried that. And that tends to help sometimes. It depends on the problem, depends on the network, but it's definitely something you can try. And that especially might help when you're in this box. But yeah, that's a good trick. All right, so the takeaway about fine-tuning is that you should really use it. It's a really good idea. Yeah, so that it works really well in practice. You should probably almost always be using it to some extent. You generally don't want to be training these things from scratch unless you have really, really large data sets available. In almost all of the circumstances, it's much more convenient to fine-tune an existing model. And by the way, Café has this existing model view where you can download many famous ImageNet models. Actually, the residual networks, the official model got released recently, so you can even download that and play with it. That'd be pretty cool. And these Café model zoo models are sort of like a little bit of a standard in the community. So you can even load Café models into other frameworks like Torch. So that's something to keep in mind, that these Café models are quite useful. All right, any further questions on fine-tuning or transfer learning? Yeah?
Yeah, I just have a question. So you're talking about like for different types of images, you might want to pull lower level layers into like the FC4096 layer or whatever. But isn't it true that at lower levels you just have like a huge number of features?
Yeah, that's true.
Like 3-dimensional box?
Yeah, so that's true. The feature dimension is quite large at lower dimensions. So you might try a highly regularized linear model on top of that, or you might try putting a small COMNet on top of that to maybe reduce the dimensionality. You can get creative here, but I think that there are things you can try that might work for your data, depending on it. All right. So I think we should talk more about convolutions. So for all these networks we've talked about, really the convolutions are the computational workhorse that's doing a lot of the work in the network. So we need to talk about two things about convolutions. The first is how to stack them. So how can we design efficient network architectures that combine many layers of convolution to achieve some nice results? So here's a question. Suppose that we have a network that has 2 layers of 3x3 convolutions. So this would be the input, this would be the activation map in the first layer, this would be the activation map after 2 layers of convolution. So the question is, for a neuron on this second layer, how big of a region on the input does it see? So this was on your midterm, so I hope you guys all know the answer to this. Murmurs? Anyone? Okay, guess maybe that was a hard midterm question. But this is a 5x5, and it's pretty easy to see from this diagram why. So that this neuron after the second layer is looking at this entire volume in the intermediate layer. So in particular, this pixel in the intermediate layer is looking at this 3x3 region in the input. So when you average across, when you look at all 3 of these, then this layer, this neuron in the third layer is actually looking at this entire 5x5 volume in the input. Okay. So now the question is, if we had 3 3x3 convolutions stacked in a row, how big of a region in the input would they see? Yeah, good. So the same kind of reason, that these receptive fields just kind of build up with successive convolutions. So the point here to make is that 3 3x3 convolutions actually give you a very similar representational power, is my claim, to a single 7x7 convolution. So you might debate on the exact semantics of this, and you could try to prove theorems about it and things like that. But just from an intuitive sense, 3 3x3 convolutions can represent similar types of functions as a similar 7x7 convolution, since it's looking at the same input region in the input. So now actually we can dig further into this idea, and we can compare more concretely between a single 7x7 convolution versus a stack of 3 3x3 convolutions. So let's suppose that we have an input image that's h by w by c, and we want to have convolutions that preserve the depth, so we have c filters, and we want to have them preserve height and width, so we just set padding appropriately. And then we want to compare concretely what is the difference between a single 7x7 versus a stack of 3x3. So first, how many weights do each of these two things have? Anyone have a guess on how many weights the single 7x7 convolution has? You can forget about biases because those are confusing. I heard some murmurs, but so my answer, I hope I got it right, was 49c squared, because you've got this 7x7 convolution. Each one is looking at a depth of c, and you've got c such filters, so 49c squared. But now for the 3x3 convolutions, we have 3 layers of convolutions. Each filter is 3x3 by c, and each layer has c filters. When you multiply that all out, we see that 3 3x3 convolutions only has 27 c squared parameters. And assuming that we have ReLUs between each of these convolutions, we see that the stack of 3 3x3 convolutions actually has fewer parameters, which is good, and more nonlinearity, which is good. So this kind of gives you some intuition for why a stack of multiple 3x3 convolutions might actually be preferable to a single 7x7 convolution. And we can actually take this one step further and think about not just the number of learnable parameters, but actually how many floating point operations do these things take? So anyone have a guess for how many operations these two take? Guess not? Sounds hard. Right, so actually this is pretty easy because for each of these filters, we're going to be using it at every position in the image. So actually the number of multiply adds is just going to be height times width times the number of learnable filters. So you can see that actually over here, again, not only do we have, so comparing between these two, the 7x7 actually not only has more learnable parameters, but it actually costs a lot more to compute as well. So the stack of 3x3 convolutions, again, gives us more nonlinearity for less compute. So that kind of gives you some intuition for why actually having multiple layers of 3x3 convolutions is actually preferable to large filters. But then you can think of another question. You know, we've been pushing towards smaller and smaller filters, but why stop at 3x3, right? We can actually go smaller than that. Maybe the same logic would extend. You're shaking your head? You don't believe it?
You don't get the receptive field.
That's true. That's true. You don't get the receptive field. So actually, what we're going to do here is compare a single 3x3 convolution versus a slightly fancier architecture called a bottleneck architecture. So here, we're going to assume, again, an input of HWC. And here, we can actually do, this is a cool trick. We do a single 1x1 convolution with C/2 filters to actually reduce the dimensionality of the volume. So now this thing is going to have the same spatial extent, but half the number of features in depth. Now, after we do this bottleneck, we're going to do a 3x3 convolution at this reduced dimensionality. So now this 3x3 convolution takes C/2 input features and produces C/2 output features. And now we restore the dimensionality with another 1x1 convolution to go from C/2 back to C. So this is kind of a funky architecture. This idea of using 1x1 convolutions everywhere is sometimes called network in network, because it has this intuition that a 1x1 convolution is kind of similar to sliding a fully connected network over each part of your input volume. And this idea also appears in GoogleNet and in ResNet, this idea of using these 1x1 bottleneck convolutions. So we can compare this bottleneck sandwich to a single 3x3 convolution with C filters and run through the same logic. So I won't force you to compute this in your heads, but you'll have to trust me on this, that this bottleneck stack has 3¼ C² parameters, whereas this one over here has 9 C² parameters. And again, if we're sticking ReLUs in between each of these convolutions, then this bottleneck sandwich is giving us more nonlinearity for a fewer number of parameters. And actually, so similar to we saw on the 3x3 versus 7x7, the number of parameters is tied directly to the amount of computation. So this bottleneck sandwich is also much faster to compute. So this idea of 1x1 bottlenecks has received quite a lot of usage recently in GoogleNet and ResNet especially. Yeah?
What's the point of the last 1x1? Like you have these columns of C/2 and you're just smearing the same information over.
Well, those convolutions are learned. So you might think of it as, sometimes you think of it as a projection from like a lower dimensional feature back to a higher dimensional space. And then if you think about stacking many of these things on top of each other, as happens in ResNet, then coming immediately after this one is going to be another 1x1. So you're kind of stacking multiple 1x1 convolutions on top of each other. And a 1x1 convolution is a little bit like sliding a multi-layer fully connected network over each depth channel. You'll have to maybe think about that one a little bit. But it turns out that actually you don't really need the spatial extent. And even just comparing this sandwich to a single 3x3 conv, you're sort of having the same input-output volume sizes, but with more nonlinearity and cheaper to compute and fewer learnable parameters. So those are all kind of nice features. But there's one problem with this, and that's we're still using a 3x3 convolution in there somewhere. And you might wonder if we really need this. And the answer is no, it turns out. So one crazy thing that I've seen recently is that you can factor this 3x3 convolution into a 3x1 and a 1x3. And compared with a single 3x3 convolution, this ends up saving you some parameters as well. So then you might, if you really go crazy, you can combine this 1x3 and 3x1 together with this bottlenecking idea, and things just get really cheap. And that's basically what Google has done in their most recent version of Inception. So there's this kind of crazy paper rethinking the Inception architecture for computer vision, where they play a lot of these crazy tricks about factoring convolutions in weird ways and having a lot of one-by-one bottlenecks and then projections back up to different dimensions. And if you thought the original GoogleNet with their inception module was crazy, these are the inception modules that Google is now using in their newest inception net. And the interesting features here are that they have these one-by-one bottlenecks everywhere, and they actually have these asymmetric filters to, again, save on computation. So this stuff is not super widely used yet, but it's out there, and it's in GoogleNet. So I thought it's something cool to mention. So the quick recap from convolutions and how to stack them is that it's usually better, instead of having a single large convolution with a large filter size, it's usually better to break that up into multiple smaller filters. And that even maybe helps explain the difference between something like VGG, which has many, many 3x3 filters, with something like AlexNet that had fewer, smaller filters. Another thing that's actually become pretty common, I think, is this idea of one-by-one bottlenecking. You see that in both versions of GoogleNet and also in ResNet. And that actually helps you save a lot on parameters. So I think that's a useful trick to keep in mind. And this idea of factoring convolutions into these asymmetric filters, I think, is maybe not so widely used right now, but it may become more commonly used in the future. I'm not sure. And the basic overarching theme for all of these tricks is that it lets you have fewer learnable parameters and less compute and more nonlinearity, which are all sort of nice features to have in your architectures. So if there's any questions about these convolution architecture designs? Too boring or too obvious?